Okay? So quantum mechanics is not wrong. These correlations really exist, and we can't explain them without some sort of information transfer instantaneously across a distance. But before you ask, no, we cannot use these correlations to send signals faster than light, okay? Because that's the obvious thing which you'd think of, that this sounds fantastic, information transfer instantaneously across the distance, but we can't use it to send signals faster than light because it just doesn't work like that. And it would require a lot to explain exactly why it doesn't work like that, but you'll have to take my word for it that unfortunately we can't use this for sending something faster than light. Okay, so that's the answer though. These weird correlations really do exist. Now, I'm sure a lot of you have heard about these correlations. I'm sure a lot of you have heard about these correlations. And so in the magazines, for example, you often hear, like New Scientist or something like that, they try to explain these correlations as being something like having two dice, and one of them is in one room, and one of them is in another room, arbitrarily far away. And when you roll those dice, they always come up the same. So they always come up showing a 1 or a 5 or whatever. Okay? So is that what these Bell correlations are like? Unfortunately, no. Okay? This is, in fact, exactly what Bell correlations are not like. Okay? So certainly if you had dice which were like this, well, that would be pretty weird. Okay, and I'm sure you could probably win a lot of money by gambling with people with them or something like that. Okay, but they actually is possible to explain those correlations, right? You could ask an engineer and give them millions of dollars and say, build me a pair of dice like this, and they could do it, right? You just put little tiny motors inside the dice, and which keep track of the time, and whenever the dice is thrown, that little motor gives little bumps to the dice and makes sure that when the die comes down and lands, that it comes down with a particular predetermined face up, okay? And if those two dice are built identically, then they'll always come down the same. All right, so that's possible. It's possible to build that with just everyday engineering, no crazy action at distance needed. All right, we can explain those results. However strange they might seem, we can explain it. And this is exactly what Einstein thought quantum mechanics could be like. Okay, on the face of it, we have these strange correlations, but there'll be some way that we can imagine there's something going on inside the particles which is determining what the results are coming out when we do measurements, and we will, if we think about it hard enough, be able to work that out. We'll understand what the hidden mechanism is. Okay? So the crazy thing is that Bell's theorem proved him wrong. Okay, not by saying, oh, this idea doesn't work or that idea doesn't work, right? He proved that no possible explanation could ever work. Okay, and that's the genius of Bell's theorem. Is not that it criticized any particular theorem, but showed that no theory like this could ever do those correlations. Okay, so Einstein's idea was pretty good, but no dice. Okay, doesn't work. All right. So what are actual Bell correlations then? They have to be something which are more subtle than this idea of just a pair of dice always coming up the same way. And so what I'm going to try to explain to you is what those correlations are really like. Okay, so most people when they give a talk about those, they'll just say, okay, so they're very complicated, you'll never understand. Just trust me. I'm actually going to try to explain it to you. Okay. So the way I'm going to try to explain it is in terms of a game. Okay. So it's a game with a single team. Okay. So it's not a team versus another team. It's just one team versus the referee, if you like. And that single team though comprises two players. Okay. So we have two players playing the game. According to the normal rules of reality, when they play the game, some of the time they're going to lose. Okay. But with these spooky quantum correlations, they can break those rules and win every time they play. And so we're going to prove that by doing this, if we can actually do this in an experiment, prove that the matrix exists, this hidden something very weird going on underneath everyday reality, by considering a matrix, so this is the third time a matrix appears here, a matrix that can't exist. All right? So this is a proof of Bell's theorem that's due to the Indian-American physicist P.K. Aravind, and he's saying, so Bell's theorem can be proven in many different ways, which is certainly true. This is my proof, which I published in 2002. Okay, and I just think it's the easiest one to explain, so that's the reason that I've chosen it here. All right, so it involves this matrix. Okay, so this is not related to any of the, like the matrix in quantum mechanics before. This is just an ordinary matrix of numbers like this, 3 by 3 matrix. And in this case, every entry is either a 0 or a 1. So it's a pretty simple matrix. So it has 9 entries, obviously. What we want for this proof is to consider something which I'm going to call a magic matrix. Okay? So the magic matrix has this property. Each column has an even number of 1s, and each row has an odd number of 1s. Okay, why do I call it a magic matrix? Because it can't exist, okay? It's not possible to have a matrix with this property, where each column has an even number of 1s and each row has an odd number of 1s. Can anyone tell me why? Why couldn't you, if I told you go away and write down a matrix that has that property? Okay, can anyone see an easy way to see why at least one row or column must fail to satisfy these requirements, which in this case is this row here, okay? So remember, so each row is supposed to have an odd number, so there's an odd number, there's an odd number, but this is an even number. The columns are all fine, okay? This has 0 1s, which is an even number, this has 2 1s, which is an even number, and this has 2 1s, which is an even number. So think about the total number of 1s in this matrix, okay? So by the requirement that all the columns have to, where are we? Each column has to have an even number of 1s. Then if I add up an even number plus an even number plus an even number, I get an even number. Yep. But by the requirement that each row has an odd number, if I add an odd number plus an odd number plus an odd number, I get an odd number. Okay? So it's impossible to have a number, the number of 1s can't be both even and odd, therefore this is an impossible matrix. Okay, so how are we going to build a game around this impossible matrix? So we're going to have 2 players, and their names I'm going to call Rowan and Colin, and you'll probably guess pretty quickly why I call them Rowan and Colin. They have to convince us, the referees say, that they own one of these impossible magic matrices. Okay? So we can't just ask them, well, okay, what's the magic matrix then? Because we know, okay, that's a game they'll never ever be able to win, okay? Because it's impossible for them to tell us. So we have to give them a fighting chance, right? So what we're going to do to make life, possible for them, we won't ask the whole thing. What we'll just ask for, we'll ask Colin for 1 column, and Rowan for 1 row, right? So of course, when Cole answers, all right, the column that he gives should obviously have an even number of 1s because it's supposed to be a magic matrix which satisfies this. And row, when he tells us our row, it should obviously have an odd number of 1s in it, okay? And of course, the common entry of the two, the column and the row, should agree. Otherwise, they're obviously not thinking about the same matrix. So here's an example where we asked Cole for column 1 and row for row 2. Okay, and Cole said 0, 0, 0, and Row said 0, 1, 0. Okay, so in this case, they won. Okay, it all worked out fine because there's an even number of 1s here, i.e. 0, and an odd number here, and this common entry is agreeing. Okay, so here's an example where it worked. Okay, so yes, I think I explained all that. Right, so if Cole and Row, the players, are just in the same room, then now the game is too easy for them to play. Okay, they can just they'll both hear each other's questions. So Cole, for example, could always answer 0, 0, 0, and Row could always give an answer which has a single 1 and 2 zeros. And all they have to do is make sure that that the 1 doesn't clash with the 0 that Cole has said. But if they both know what they're being asking, then that's a very easy thing for them to do. Okay, so this makes the game too easy. So to make the game harder, what we're going to do is put Cole and Row in distant rooms. Let's even say they're concrete bunkers, okay, so that there's absolutely no way for them to communicate with each other. They can't use their mobile phones or whatever. It's all completely isolated. So here they are, looking pretty stressed, as you can see. So this is Cole over here, Row over here, and these are our interrogators. They're going to ask them these questions. So then at the same time, the interrogator over here asks Cole for column 1 and Row for row 2. So in this case, Cole says 0, 0, 0, for example, and Rho says 0, 1, 0, is it going to work? Yes, okay, that's the example which we had before, so that's going to work. But can they always win? All right? Can they always win in a game like this? Well, if you think about it, what is actually involved for a game like this is that they have to, because they haven't heard each other's questions, okay? They have to agree beforehand, essentially, or have an idea, a plan beforehand about how they're going to answer any individual question which they are asked. Okay? So in other words, they have to know before they're measured, right, what result it is, what they're going to say. Okay? But of course, agreeing what answer they're going to give in any particular trial means that they, for any of the three questions, means that they have to know, agree upon essentially what answer they're giving to every single entry of the matrix, this 3 by 3 matrix, right? But they can't always win because this matrix doesn't exist. Some of the time, they're going to have to give incompatible answers. And in fact, if you think about it a little bit, because it's always possible to have, no problems, put all the problems in one last entry in the matrix, there's 1/9 of the time they're going to have to fail. Okay? So it can be as low as 1/9. If they're bad players, it might be more than 1/9. But they're always going to fail, on average, at least 1/9 of the time. So if you play this hundreds of times, then 1/9 of that, they're going to fail. So for example, here, if Cole is asked for column 2 and Rho is asked for row 2, and they answer like before, okay, that Cole just says 0, 0, 0, and Rho says 0, 1, 0, now it's a failure, okay? Because they don't agree on this common entry here. And that's going to happen, as I said, at least 1/9 of the time. Okay, but what if Cole and Rho are these super agents, these quantum physicists, that can share entangled pairs of particles? Okay, so what Aravind showed is if Cole and Rho share pairs of entangled particles, they can win this game 100% of the time. Okay? And it doesn't matter how far apart they are. It doesn't matter how much effort is put into making sure that there can be no communication between them. They can still win. Okay? And so the way they do it is that what they need is a device which can make 3 different types of measurements on a quantum particle. And so the quantum particle, for each time they have to play the game, they have to have a different pair of entangled particles. So there actually have to be lots of quantum particles in here. But they all come in pairs, okay, entangled pairs. And when they're asked a question, remember they're only asked one of 3 questions. It's like column 1, column 2, column 3, or row 1, row 1, row 2, row 3. So there are 3 possible questions they can get answered. And then, but there are, if you think about it, there are actually 4 possible answers that they could give, which are consistent with having to have either an even number or an odd number of 1s. So what the device looks like is that there are 3 buttons to press and 4 little lights which go off. Okay, and we assume that this guy can't see the lights because he's got glasses on, and they can get away with it. Okay, so for example, when the interrogator is asked what's column 2 and what's row 2, then the Cole presses 2, and Rho in this case presses 2 as well. Lights flash up on the various things, and based on what those lights are, they know the code. They know that means Cole will say 1, 1, 0, and Rho will say 1, 1, 1. Okay, and when I put them together, they match up. The common entry is always guaranteed to match up, so they can win 100% of the time. Now, so quantum entanglement lets them break the normal rules of reality. Okay, this was a task that was impossible, except that if they're quantum physicists, if they're these super agents, they can do it. Now, of course, I haven't, by showing you this slide, that's not a proof that this is true. You just have to believe me that this is true. But my aim wasn't to explain to you how the maths of quantum physics, gives you this result. My aim is just to convince you that the correlations you get really are very strange, okay, and that what you get from quantum physics is something you can't get from anything else.